Hi, I'm Yonatan Winetraub from Team SpaceIL, and I will be talking today a little bit about our landing site and control for the lander for the 500 meters requirement to travel on the surface or above the surface of the moon. We're now doing an analysis for the landing sites. We're just finalizing, selecting few landing sites, few possible landing sites for the vehicle, and we're now, I would like to talk a little bit about the lander itself and the control we're doing for it. So our goal here in the landing site is to land on the flattest surface we can find. We don't want to land on mountain hills or mountain sides. We just want to aim for the flattest surface we can find. So the vehicle itself can land in an upright position on the ground and not risk it in that direction. However, since our vehicle is so small, relatively small rocks that are hard to find from space or to map from space, we can land on one of those and have one or more of the legs landing on one of the rocks. So rather than having an upright position as this one, we might find ourselves landing in that angle with a small tilt towards the surface of the moon, for example, a tilt like this. Now this is not a problem for the legs itself, but it is a problem for the control algorithms. For example, our lander is actually a hopper. We're going to meet the 500 meter requirement by doing a hop, and we're going to reignite the main engine and let it travel for 500 meters to meet the requirement. However, if the landing site analysis shows that on that direction we have rocks or rough terrain, we might have a problem with that tilt, because once we ignite the main engine and apply force in that direction, the vehicle itself will accelerate towards that end, which might be tricky. So we want to, let's say we want to have the possibility to travel in any directions once we land. For example, we can find that on that end of the moon has a flat surface, and we want to land there to do the hop in that direction. So we want to have the algorithm capable of tilting the spacecraft and travel in that direction. So the algorithm itself will start off by doing a short burn to lift the vehicle off the ground, and throughout this burn the control algorithm tilt it to an upright position. So the scheme works pretty much like that, and the vehicle itself is traveling upwards in the end. Now, once we go upwards, we want to tilt the spacecraft towards that end, towards that direction, and then reignite the main engine to do a longer burn that will give us the delta V required to meet the 500 meters requirement on that direction. Now, you probably remember from high school senior year, the optimum angle for the delta V is 45 degrees. In that angle, you're traveling the first distance on air, and 45 degrees, your delta V, you will be traveling as much distance towards the horizontal way. So we want to give the vehicle a delta V at an angle of 45 degrees. However, since our engine has a finite amount of force it can apply to the spacecraft, we cannot tilt the vehicle to 45 degrees, because it has to contradict the force that the gravity applies as the engine burns. So you need actually to have an angle that is smaller than 45 degrees, and a few angles, not a lot. So it will have once the engine is burning, at the end of the burn, you will get the delta V in the desired direction, and afterwards you're flying and you can land 500 meters on that end. And this is the analysis we're doing right now. We're also looking for guys with control backgrounds or interested in control, as well as landing site, to join to the team. If you would like, you can apply at www.spaceil.com or send an email to contacts@spaceil.com. And you're more than welcome to follow us on Twitter and Facebook under Team SpaceIL. Thank you very much. This has been our update for this week, and we'll do a little more of these in the future.